not particularly successful, trying to move us from this ethereal conversation of electric potentials to a more pragmatic conversation about circuits. I don't know that I really nailed what I was hoping for in that conversation. So today, I'm going to be far more direct. I want to talk about how to solve circuits. And solving a circuit changes depending on the nature of the circuit you're attempting to solve. But in general, the solution to all circuits can come from something called Kirchhoff's laws. And I'm spelling the name wrong because I don't know how to spell it. It's got a couple of H's, I think, a couple of F's, I don't know. It's a mess. I never spell it the same way twice. And when one of you invariably looks it up and tries to correct me, it makes me want to spell it even worse. So don't bother, because I don't care enough, and I just find it to be a little bit arrogant of you to try to correct me. So when I learned this, by definition, we know that a capacitor equals Q over V, which means that a capacitor in a circuit will have a voltage equivalent to Q over C. Now, the reason that's important is how we deal with capacitors in a circuit. We're going to look at what's called a series circuit. This is a series circuit, meaning in this circuit, my circuit elements, oh my God, let's try this again. So this is a series circuit in that the circuit elements are located one after another. I want to contrast that just a bit with a parallel circuit so you can understand the difference. So the circuit on the left is considered series. I have two capacitors located in series, meaning they are one after the other. Bless you. But the circuit on the right would be considered parallel, in that the line of current splits and is divided so that some of the current goes through one side while some goes through the other. I think parallel probably has meaning to you already, and you can probably see the elements of why they would call one a parallel circuit versus a series circuit. Now, saying the whole circuit is series or parallel really is an oversimplification. These two elements are in series, and these two elements are in parallel. So there's no problem with having a circuit like this. Where we have circuit elements that are both in series and in parallel. So what would you call that? It's just a circuit. They're all just circuits. But you can have elements that are in series and elements that are in parallel. Also, it doesn't have to be just capacitors. I could have a capacitor and a resistor. And we'll get to what resistors are in the future, but this would be a series circuit. These elements are in series. The difference is that capacitors deal with voltage differently than resistors deal with voltage. Kirchhoff's law applies to all circuit elements, as long as you know how they deal with voltage and how they deal with current. And if not current, charge. So we're going to focus on some simple circuits. And what I'm eventually going to teach you is a process known as stepwise reduction. But stepwise reduction is a simplification of Kirchhoff's rules. Kirchhoff's rules themselves generate relationships in the same way that you guys who are in mechanics know that Newton's laws generate relationships. Those relationships may be able to be used to solve for the motion of an object. In circuits, Kirchhoff's rules will generate relationships. And at the end, you hope that those relationships will allow you to solve a circuit. Solving a circuit, what I mean by that is being able to express what each circuit element is doing in the circuit. That's what solving a circuit is. Being able to express what each circuit element is doing. So if I say solve the circuit, I should be able to point to any circuit element. You should be able to tell me the following kinds of things. The voltage across that circuit element. The current through that circuit element. The energy stored in that circuit element. The power consumed by that circuit element. I'm saying them all because you guys weren't writing it down anyway, so I can say that list as quickly as I want. But if you want, I'll narrow it down for capacitors. When I say solving a circuit when it comes to capacitors, it should be clear that I'm looking for three things. Because these are the three things that involve capacitors. The voltage across the capacitor, the charge stored on the capacitor, and the energy stored in the capacitor. Solving a capacitor circuit will be for those three things. So voltage, charge, and energy. In the future, I will want you to be able to do that as a function of time, because we'll deal with transient circuits, circuits that change over time. But for the current discussion, we're going to assume that our circuits exist in two states. The state before the potential difference is connected, and what's known as the steady state. You're going to need to learn this phrase. The steady state condition. So for today, we're going to be solving steady state conditions. We know that capacitors have to be charged, and that means that the charges have to build up on the capacitor over time. Generally, what we say in a situation like that is I would like you to find the voltage across the capacitor after it has been connected for a long time, or after the switch has been closed for a long time. That phrase, for a long time, basically means an infinite time scale according to the circuit, meaning your capacitor reaches its full charge. It's important to understand that because later on we're going to prove how long that time scale is, and you'll come to understand that infinity in circuits generally is measured in microseconds and milliseconds. That's long enough. So for the time being, we assume the steady state of the circuit, meaning it's been connected for a long time and your capacitors are fully charged. All right, that's a long way to get to where I want to go, which is to talk about how to deal with Kirchhoff's laws. And Kirchhoff's first rule is really simple. It's called the voltage rule, and I can state it in a single sentence. Application is more complicated, but I can state it in a single sentence. Ready? All right, Kirchhoff's first rule. The sum of the voltage drops in any loop through your circuit equals 0. The sum of the voltage drops through any loop through your circuit will equal 0. Now, I just want you to know that's a super oversimplification. And we will have to adjust that rule. So you should probably mark where it is in your notes so you can come back to it. Because right now I'm going to deal with circuits that are super easy. But as our circuits become more complicated, we will need to become more flexible. Now, I have to augment that rule. I mean, I have to add what I mean by parts of it. Every element in a circuit is considered is considered a voltage drop. Some circuit elements add voltage, some circuit elements take away voltage or are a drop in voltage. Going from the minus sign to the positive sign of any battery is an increase in voltage. Going from the positive sign to the negative sign of a capacitor is a voltage drop. It's a decrease in voltage. This is not always obvious. And so sometimes you have to kind of reason out your circuit ahead of time. Now, I don't think this circuit is particularly hard to understand. I think that it's probably not too unobvious that this plate will become a positively charged plate when connected to the battery after I let it stay connected for a long time. And that this plate will become a negatively charged plate when it's been connected to the battery for a very long time. If you don't understand why, think of it as one capacitor for a minute. One huge air-gapped capacitor. If this were my capacitor and I connected it up to a voltage supply, I don't think it's a huge stretch to realize that it's going to take away the positive charges from this side of my capacitor and deposit them there. That's the direction of current flow. And every time it takes a positive charge from that plate, it makes the bottom plate more negative. And every time it deposits a charge on the top plate, it makes that top plate more positive. So the potential difference pushes charges, and it pushes positive charges in a particular direction, so that this will become positively charged and this will become negatively charged. If I have plates here in the middle, do you realize that as this plate becomes more positively charged, it's going to push positives away from the plate right below it? Right? They will be repelled away, which is why positive charges will flow down here to the bottom plate. That's why these inner plates that we're talking about will become negatively charged here and positively charged there. Does that make reasonable sense to all of you? Good. So, a loop. When I talk about Kirchhoff's law, a loop is any path through a circuit that starts in one place and ends back in that place. For example, I could start here, and I would encourage you to do this the way I'm going to do it, which is draw your loop with an arrow in the direction of the power supply, in the direction of the applied potential difference. So I will start my loop there, intentionally drawing it like this, so that I can use the direction of the power supply to help establish the direction of my loop. Trust me when I say in the future, you want to go in the direction of the applied voltage. It will help determine the direction of the voltage drops of your circuit. Yes, Oliver?
Is it possible for the capacitors to ever have differing directions of charge? Is it ever possible for it to be like positive, negative, or negative, positive?
Ever positive? Sure. I'm sorry, ever possible? Sure. I don't know how you would get there necessarily from this circuit, but I am sure there are ways you could do that. It might be less effective than you think, though. But we're going to see a possibility where that could occur, so give it time. All right? Now, Kirchhoff's laws here are pretty straightforward. They tell us what to do. They tell us to create a relationship. And that relationship is just about voltages. It tells me that first start with my voltage source. So I'm doing this in the order that they exist in the circuit. So that's the voltage applied to the circuit. And then subtract any voltage drop. So my first voltage drop is the voltage across capacitor 1. So I'll put a 1 at the bottom to remind me this is referring to capacitor 1. And then I'm going to subtract voltage 2, because I go through one capacitor, and then I go through another capacitor. And now I am back to my start, so that has to equal 0. Now, we only had one loop through the circuit, but it creates this relationship. Now, the next step in trying to solve a circuit after you've applied the after you've applied the voltage loop to your circuit, is to check and make sure that every circuit element has been taken in by the loop you chose. Now, this is a simple circuit. There was only one possible loop through the circuit, so we got every one of the elements. So now that we have accomplished that, we have made sure we've taken in every circuit element here. Now apply your rules for voltage to each element in your circuit. I have rules for voltage that apply directly to capacitors. So the next thing you do is you apply your rules directly to each element. So I will say V minus Q over C, 1. Actually, I'm probably going to put Q1 over C1 minus Q2 over C2 and set that equal to 0. Now, this produces a relationship, and this relationship may or may not be used to solve your circuit, but it tells us information about the circuit. And it helps us deal with what's called equivalent circuits. But this is how Kirchhoff's laws will be applied to our circuit elements. Now, there's more I want to show you here, but I want you to try this on your own in practice real quick. Although it doesn't seem like we've done very much, I'm thinking baby steps works best here. So here's what I'm going to do. We're going to know that over here, we're going to have to use some similar logic to come up with what the equivalent capacitance is for capacitors in series. And then we're going to be solving circuits. Tomorrow, we're going to be solving circuits. We're going to do a bunch of them. This is the one that was in series. And we don't have a way of doing equivalent capacitance yet for series. We didn't get that far. But we do have this relationship here, which shows us that in our series circuit, the potential difference would be equal to Q1 over C1 plus Q2 over C2. Our goal here is to try and figure out a way of writing out the equivalent capacitance for our system in series. And this one's not as straightforward. It might take a little more careful consideration. And it involves looking at this picture a little bit. Now, remember, our goal here is to come up with a equivalent circuit. So we're trying to take this circuit from 2 capacitors to 1 capacitor. Now, the first thing that might not be obvious is, again, whatever this equivalent capacitance is, we know that the voltage would have to be Q total divided by C equivalent. That would have to be true. So in a similar substitution from before, I could write this as Q total over C equivalent equals Q1 over C1 plus Q2 over C2. This part, though, this part might be hard for you to, come on, just do what I ask. This part might be a little bit harder for you to follow, so pay careful attention. I said this yesterday, but I want to reiterate it. If one charge is taken from this bottom plate, one positive charge is taken from this bottom plate and moved to the top plate, then the top plate has received one charge and the bottom plate has revealed one negative charge. Now, by a similar deduction, a positive charge that is here would be repelled away from the positive charge that was deposited on the top plate and therefore would travel to the bottom plate, revealing a negative charge on the top portion of that section, I guess. Now, what I'm trying to infer here is that there is a conservation of the movement of charge, a one-to-one correspondence. So whatever number of charged particles removed from the bottom plate to the top plate, it assures us that the charge on both of these capacitors has to be the same amount. Which brings me to a new rule. The charge on capacitors in series are all the same. if you have a group of capacitors in series, they will all have the same amount of charge. The charge on capacitors in series is all the same. Always. So that means here, the total charge and the charge on each capacitor must all be the same number. It's got to be the same total charge on all of them. Meaning the equivalent capacitance obeys this kind of weird inverse relationship. Yes, Jeremy.
Why isn't the total charge 2?
How much charge was moved by the potential difference in order to satisfy what happened? I understand why you're saying that, and that's why I was trying to be very careful about this. Remember, we're talking about this, we're not comparing how much total charge there is on the individual capacitors, which is 2Q. If I was to cut the lines here, and Jeremy's actually asking a question to which it's probably important for you to write this down. I said two different things, and I want to make sure that you understand that they were different. If once this is charged up, let me get all this distraction out of the way. If once the system was charged up, I cut the cables here, those capacitors would retain their amount of charge, and they would each have the same amount of charge. The total charge then would be 2Q amongst both capacitors. That's true. But the potential difference didn't move 2Q worth of charge. The potential difference only moved 1Q worth of charge. From the standpoint of the battery itself, it moved just Q. It was the influence of that electric field that moved the amount of charge that happened between those two plates, or between those two capacitors. You follow me so far? So if we were to replace this capacitor with an equivalent capacitance, something that the battery couldn't tell was any different, it would still have moved the same amount of charge. You understand the difference here? I'm trying to be very careful, because if I took these two capacitors, disconnected them, and reconnected them in parallel, then I would be able to use those charges differently. So it's a good question, but you need to be careful about this. Capacitors in series all will have the same amount of charge on them, but the potential difference only moved that amount of charge, not the total for all the capacitors. I'll say it again. Only one positive charge was moved from here to here. It's a weird thing, I know. So I want to go someplace and sum this up for a minute. So maybe not. So capacitors in series, they all have the same charge. And the equivalent capacitance is found by adding up the inverses and then inverting. Doesn't matter how many are in series. You add up all the inverses, and then you invert your answer. You will forget to invert your answer. So don't. I'm telling you not to. Not that me telling you not to makes a bit of difference. You just try not to. And in parallel, they all have the same voltage. And their equivalent capacitance is the simple sum. Now, this was derived using Kirchhoff's laws. And truthfully, we could use Kirchhoff's laws to solve circuits, meaning to find the individual charges, the individual potential difference in total energy on each capacitor, but it's so much easier to just use these derived rules. The whole reason I talked about Kirchhoff's laws was so that I could get to these two rules. And once you have these two rules, it's pretty much a straight shot to solve circuits as long as they conform to series and parallel. That's the thing I need to be very clear about. You can solve circuits using these two rules, but your circuits have to conform to series and parallel. I know you don't know what that means yet. Let's take a look at what it will mean for us. Let's start by trying to understand what I want you to do. And we're going to put some numbers to this so that you can have this experience. We're going to do two different circuits real quick. And no longer am I going to just do esoteric ideas. We're going to put numbers to it. So I've got a 3 microfarad capacitor, a 6 microfarad capacitor connected in series to a 12-volt power supply. I'd like to find the charge and the energy and the potential difference for each capacitor in the system. Now, the way this is done is a process called stepwise reduction. Stepwise reduction. Again, we could use Kirchhoff's laws, but it's harder to actually do the work using Kirchhoff's laws than it is using stepwise reduction. So we're going to use stepwise reduction to do this. And the first part of stepwise reduction is to reduce your circuit down to a single capacitance by using the rules of series and parallel. In this example, that's going to be a single step, but we're going to work up to more complicated circuits today. Just trying to show you the process. So in this example, we have one set of capacitors that are in series, and we want to reduce it down to a circuit that has a single equivalent capacitance. So I'm writing a stepwise reduction. I'm finding a series element in the circuit, and I'm suggesting to myself I could reduce them down to a single capacitance. I'm going to bring the battery over because the battery doesn't change. But I'm going to use my rules for series circuits to figure out the equivalent capacitance by doing 1 over C equals 1 over 3 plus 1 over 6. As long as they're in the same units, I don't have to do any conversion. My answer will also be in microfarads. Now, my experience has been that most students know how to add fractions together. I assume you guys are no different, so you could probably do this all on your own. I'll wait, because I've done this before, and I have reason to have doubts. Besides, I read the news. They say none of you learned anything for the last 2 years. Luckily, you learned this in the 2nd grade. So the answer is 2. I can see it on your face. Yep. Practice. The answer is 2. I'll wait, but I don't want to wait long. How can you have a question? I believe you. I believe there's going to be a question. What could I than we did before? We have 2 capacitors there. How could we end up with a smaller capacitance? There's actually a very straightforward way to explain that. Think of capacitance again from the standpoint of its physical structure. By putting 2 capacitors in series, we've effectively increased the total gap between the plates of the capacitor. In the same way that putting them in parallel increased the total area available to the capacitor. So that's actually a relatively straightforward question to answer. But there's actually a more complicated answer too. And that more complicated answer has to do with neither one of these capacitors gets to actually use the entire voltage. Their effectiveness in the circuit is reduced because they only get a portion of the voltage. If you think of Kirchhoff's laws, the sum of the voltage drops has to be equal to 0, which means we're applying 12 volts to both capacitors, but each capacitor only gets a portion of those 12 volts. So their effectiveness is less. That's why their equivalence in this circuit ends up making them less useful or less able to store charge. So there's two ways to answer that. One is in the way in which they're being used, and one of them is the physical idea that you have more of a gap now between the plates. So I actually appreciated that question. See, Mr. Shelton, you should be more patient more often. Nah, why do that? All right, so we've reduced our circuit. Once you get down to a circuit that has a single capacitance, and I know it was a single step, but bear with me, your job is to apply the rules of your circuit element. In this case, the rule of our circuit element is Q equals CV. This tells us how much charge there is on our equivalent capacitance. Should be pretty straightforward. Now, I get that there's probably a desire to convert the microfarads into farads, but our voltage is in volts. So if you do the math on this, you'll find this is going to be 24 microcoulombs. And the math works here. So try it out for yourself, but I'm going to assume that the unit portion of this you can do on your own. Any question about that? That's just 2 times 12, so I didn't think I had to do very much there. Now, you could also go one more step, and that is to find the total energy here. I will leave this to you as an exercise, but you should do that too. 1/2 CV squared. So I don't want to spend a lot of time on that portion because I want to finish this today. So stop with the calculators and listen closely. Once you find the charge and the voltage on an individual capacitor, you can go back a step. We're going to go from here back to here. Stepwise reduction allows us to take the information we just found on this capacitor and apply it to the system of capacitors we replaced. Now, I'm going to give you a rule, but it's a rule you already know. When going back a step, judge, are you going back to a step that is in series or a step that's in parallel? In this case, it's a series step. So when you go back to a step that's in series, you apply the charge to every capacitor in series because they all must have the same charge. So I'm going to go back a step. I'm going to apply the 24 microcoulombs to both of my capacitors because they are in series. All right, we now forget about the circuit we were just at. We focus on the circuit that we have at hand. And we use what we know about our circuit elements to find the missing piece of information. We're still using the same formula, Q equals C times V, but this time we're solving for the voltage. So I have 24 microcoulombs, 3 microfarads. Should be a pretty straightforward way to figure out how much voltage is across this capacitor. 24 divided by 3, 8 volts. Go to the next one. I have 24 microcoulombs. I have 6 microfarads. 24 divided by 6, 4 volts. And better yet, every intermediate step allows you to check your work. The sum of the voltage drops had to be 12. This has to sum to be 12. A lot of ways to check your work doing circuits. This isn't like the stuff we've been doing before. Stuff ends up being pretty solid. But again, I would really like to get to at least one mixed circuit, so I'm going to move on right now. We're going to do a parallel example. So a straightforward parallel example. I'm just going to take the same two capacitors, arrange for them to be in parallel. So 6 microfarads, 3 microfarads, and 12 volts. Stepwise reduction. Now, because this is a parallel circuit, we can solve this a simpler way, but I'm trying to teach a process. So just understand that we could say it's 12 volts right now to both of those and be done. But I don't want to do it that way. I want to teach a process. So can we do that? Can you follow along with me for the process? Reduce it. That's our first step. We're going to reduce our circuit down to a more equivalent resistance. These capacitors are in parallel. Yeah.
What's resistance?
I'm sorry. I'm saying it because we're going to get resistor circuits in a minute. So if I said the word resistance, I meant capacitance. Sorry. These capacitors are in parallel. We're going to reduce the capacitance circuit down. Sorry. The rules for resistors are very, very similar. Now, we just add these up. Because these are in parallel, all you need to do is add the two capacitances together. So 9 microfarads. However, the charge, Q equals CV. Still keep doing that. So 9 times 12. I'm a little nervous that you guys may not know it. Oh, did you need a calculator for it? 108 microcoulombs.
Not even try that.
Guys, I don't have the time for this. You want one more step. Come back here. Now, again, this particular capacitor, this was kind of a waste of our time because we didn't really need to do this. But when you go from a single capacitance back to a set that's in parallel, you apply the voltage to them both. We already knew the voltage was 12 volts. But we needed to have this experience for us to do the next circuit. So I apply my 12 volts. And now you individually find the charge on each of those capacitors. 3 times 12, 36 microcoulombs, and 6 times 12, 72 microcoulombs. And they should add up to be the charge that was there before. Again, all sorts of internal ways to check your work. Now, I needed to get to this point because what I actually want to show you isn't these two circuits. It's to reduce a more complicated circuit that has multiple elements in it, parallel and series elements. And that's why we needed to see one of each so that we could do something more akin to this. Those other two would have been really easy to do with Kirchhoff's laws too, because they all had simple loops. But once you start getting to a more complicated circuit, having a means to solve it without using Kirchhoff's laws is very useful. Because Kirchhoff's laws really make these hard to do. This is going to be 3 microfarads, 3 microfarads, and 3 microfarads. I'm sticking with numbers that are relatively the same because I want to stress process. And we'll keep this 12 volts. This circuit can't be reduced in a single step. called stepwise reduction. Now, in each step, you can only reduce something that is purely parallel or purely series. So you have to find elements within your circuit that fit the profile for being parallel or series. So clearly, this 3 microfarads is in series with a system of parallel capacitors. So if we want to reduce this circuit down, we're going to have to do it in steps. Generally, when I start doing circuits like this in steps, I stop redrawing the entire circuit, and I tend to only draw the part from here to here. We're only working on the capacitor side for right now, so it becomes very distracting if you draw everything. You do it however you want, but I need it to be big enough to fill the board. So the top capacitor isn't going to be changed. It's the bottom set that's in parallel that we're going to find an equivalent capacitance for. We're going to take that set that's in parallel and find the equivalent capacitance for that set. Now this one's easy. Parallel ones we just add together. So our equivalent capacitance for that bottom part will just be 3 plus 3. Not tough. 6 microfarads. So that's our first step in our stepwise reduction. We still can't apply the voltage because we do not have a single capacitance yet. But now I have a system that clearly is pure series capacitors. So I start from here and get down to a single capacitance. I'm going to have to use the rules for series to do so. And we just did this one, so I don't think I have to go back through 1 over 3 plus 1 over 6 equals 1 over 2, and then invert the microfarads. So we have stepwise reduced our circuit to a single capacitor, and this capacitor is still being serviced by the 12-volt battery. So now we start here and work backwards. The 12-volt capacitor appears to be connected to a 2 microfarad, the 2 microfarad capacitor is connected to our 12-volt source. So we use our rule for capacitors to determine how much charge is on the capacitor. 2 times 12, 24 microcoulombs. Now, we step back a step. Our goal is to take this information back to the step just before. Stepwise reduction reduces the circuit, but now we apply the rules for series and parallel to figure out the individual values of our capacitors. So when we step back, when we have a circuit that's in series, we apply the charge to each portion of the circuit that's in series, because they all have the same charge. So I take my 24 microcoulombs and apply it to each because they are in series. I now forget the simplified circuit and only work on the 2 that are in series. I have the charge. I now need the voltage. So I'm going to try and find the voltage across each part by using Q equals CV. So that means the voltage will be the charge divided by the capacitance. So 24 divided by 3 gives me 8 volts. 24 divided by 6 gives me 4 volts. Check my work. 8 plus 4 is 12. I'm good to go. So I'm going to go back a step. Before you go back a step, identify the fact that one of these capacitors isn't going to change. So I now know this capacitor has 8 volts across it, and it must have 24 microcoulombs of charge on it. That has to be true, because this capacitor and this capacitor represent the same capacitor. On the other hand, this capacitor is this system of capacitors. So when I step back and move back to the original, I'm going from a set that was an equivalence to a set that's in parallel. Parallel capacitors see the same voltage. So I take the voltage from that capacitor and I apply it to each of the capacitors that are in parallel. Now that I've done so, I can take a minute using this and figure out the charge on each capacitor. So 3 times 4, 12 microcoulombs. 3 times 4, 12 microcoulombs. And of course, I have a moment I can check. 12 plus 12 equals the 24 that was there before. Now, folks, this is stepwise reduction. In your homework, you have several different circuits that are for practice. We're going to look at more complicated stuff on Monday, but no matter how complicated it is, it's just those 4 rules. Add them together, add the inverses, and parallel has same voltage, series has same charge. Can you use the things I've just told you to attempt to apply Kirchhoff's law to this circuit? You have 2 relationships, something like V minus V1 equals 0 and V minus V2 equals 0. I see 2 possible loops through the circuit. Actually, there are 3. But 2 that makes sense to me. There is this loop through the circuit. And there's also that loop through the circuit. I have to use more than one loop because I need to make sure I encompass each of the circuit elements. There's a third There's a third loop you could use as well. This loop makes less sense to me. It still might have its usefulness, but in this loop we don't actually encompass the power supply. But it still must work, meaning V1 minus V2 is going to have to be 0. And I'm choosing one of them to be positive and one of them to be negative because I'm pretty sure these plates are going to be positively charged and these plates are going to be negatively charged. And I go to the negative to the positive plate on a capacitor, that should be an increase in voltage. Now, there is a good reason to do this, and that I think is obvious. It shows us that these 2 capacitors have to be at the same voltage. That wasn't a surprise. They're each equal to the same voltage. And moreover, we know that we can, we can write this as V minus Q1 over C1 equals 0. And V equals Q2 over C2. I'm sorry, I don't know why I did it differently for both. I guess I'm just not thinking it through. There, minus Q2 over C2 equals 0. So, Mr. Shelton, why are you going through all of this? This seems like you're just writing letters down. There is a point I want to make, and I'm almost there, if you can just see it through with me. Is it clear to you in this circuit that both capacitors have to be at the same voltage? Is that clear to you? All right. The voltage supply doesn't know what's connected to it. The voltage supply doesn't know there's 2 capacitors there. The voltage supply merely provides a potential difference to the circuit, and will push charges to meet the demands of the circuit. Meaning there is an equivalent, I probably should write this different. There is an equivalent capacitance. An equivalent capacitance. There's a capacitor I could connect to this voltage supply that would behave like the two capacitors that are in parallel. Meaning there is a simpler fictional circuit that has an equivalent capacitance. A certain amount of capacitance that would be the same as the two capacitors that are in parallel. The reason it's important to figure out the equivalent capacitance is it gives us a method for figuring out how the circuit behaves. It's telling us what is the total capacitance of our circuit. Equivalent isn't total. They're not the same word. What it means is you could replace the two capacitors with this capacitance and the potential would still provide the same amount of charge. That's what it means to be the equivalent capacitance. And right now, that equivalent capacitance would be Q total, the total amount of charge pumped to the whole circuit, divided by C total, or C equivalent. You could use either word there, C total or C equivalent. I'll stick with C equivalent, just so that it's the same. Yeah.
So this would be like ideal path for a capacitor?
It's more like,
Most efficient?
no, neither of those are true. It's more like what if I have a requirement where I need a certain capacitance for my circuit, but I don't have a capacitor of that size. Well, maybe there's a way I can arrange capacitors in series or in parallel that would come to the same size. That's what this is about. Now, we can prove it using Kirchhoff's laws. And that's what this has been about, getting to a point where we could prove the equivalent capacitance. Now, I don't want to spend a lot of time doing that. I'm going to talk to you about equivalent capacitance. But this is where it starts. So the equivalent capacitance comes from looking at the fact that our circuit has a total amount of charge that was pumped from the battery to the capacitors. And some of that charge went to one capacitor, and some of that charge went to the other capacitor. Right? The total charge pushed through the circuit had to end up on these two capacitors. And looking at what we have here, it should be pretty clear to all of you that Q1 equals V times C1. Right? That's just this. Q1 equals V times C1. And here, Q2 equals V times C2. This gives me a method of writing how much charge was pushed to the circuit based on how big the capacitors were, instead of individual charges. I could also write the total amount of charge in terms of the equivalent capacitance. I can't write all that word. You're just going to get equiv because we're out of time. Now, I was hoping to get here faster, but I've been trying to be deliberate. But do you see something here when I combine all those together? I can cancel all the V's. They represent the value of the voltage supply. And if you didn't follow any of my conversation to this point, hear this part because it's the most important part. We don't use Kirchhoff's laws very often. We try not to. We use the results of Kirchhoff's laws, which tell me that in any circuit, if I have capacitors in parallel, the equivalent capacitance is the sum. In any circuit where I have capacitors in parallel, The equivalent capacitance is the sum. Now,